Europa is Jupiter's smallest moon, and it's believed that extraterrestrial life could lie in its subsurface oceans or liquid water lakes. Tidal flexing provides energy that drives geological processes to support ecosystems clustered around hydrothermal vents or on the underside of the ice sheets. Discovery of extraterrestrial life would allow us to understand the origination and diversification of our own life much better. Although we probably won't find complex creatures, having another form of life would allow us to widen the scope and understanding of what life is, because we currently only have one planet on which we base our definition from. Pioneer 10 and 11 provided low-resolution images of Europa's surface in the 1970s. Data collected by Galileo provided evidence for both an exosphere and saltwater subsurface oceans. The NASA Hubble Space Telescope observed water vapor above the south polar regions of Europa in 2012, providing strong evidence for water plumes. This evidence provided a solid scientific basis on which to begin our own mission. Our mission is to understand the composition of Europa's interior. This will be done by dropping geophones and the geophone orbiters to create an impact and measure the waves produced by the impact. Recorded waves will be analyzed to present the depths of each layer, as well as produce a visual representation of the layers recorded.
In order to determine the thickness of Europa's icy crust and the depth at which the potential ocean beneath exists, our mission plans to perform two seismic exploration experiments. First will be a seismic reflection, and the second will be a seismic refraction experiment that will both hopefully yield results about the subsurface of Europa. In order to perform these experiments, measuring devices and an energy source is all that is needed. Our first experiment will be seismic reflection, a process that records seismic waves that are reflected off different subsurface layer interfaces. 0.1 to 10% of a seismic wave is reflected back to the surface when a change in density occurs, indicating a new layer. When the waves reach the boundary between the water and the ice layer, the reflections will appear to stop. Waves will move much slower in the less dense liquid. Upon reflecting off the solid layer below the water and returning to the surface, there will be a large gap in the recording. Through computer analysis, the thickness of each layer can be calculated and visual representations can be produced. Our second experiment will be seismic refraction. We will be measuring waves that are refracted through the different subsurface layers on Europa. When a wave approaches an interface at its critical angle, part of the wave will travel along the interface speeding up before it exits towards the surface at an angle opposite the critical angle. That is the wave the geophones will pick up. However, we are unable to determine the liquid layer because seismic refraction cannot locate a less dense layer residing below a higher density layer, such as the case on Europa. That is where shadow zones come into our mission. Since S-waves cannot move through a liquid, when they reach the water layer, the geophones below that latitude will cease to record them, creating what is known as an S-wave shadow. P-waves can move through water, but are greatly refracted. They will enter the water, the core, the water on the other side of the core, and finally the ice layer, refracting at each interface until they reach the geophones at the surface. A shadow will also occur for the P-waves, but it will be more narrow than the S-wave shadow. Computer analysis of these shadows will allow us to determine the thickness of the ice layer, the water layer, and even the core. However, if there are no shadows found, then it will mean that there is no liquid layer on Europa. In order to record the data needed to complete our mission, we will be using geophones, placed evenly in as straight a line as possible across half the surface of Europa. They record velocities of both reflected and refracted waves at the location they are placed. The values recorded by the geophones will allow us to calculate the thickness of the different subsurface layers. A total of 210 geophones will be required. In order to relay the information recorded by the geophones, 4 transmitters will be dropped to the surface at different locations to ensure that the data makes it safely to Earth. Everything will be transmitting on X-band radio waves, which NASA's Deep Space Network. Due to the depths we plan on recording with seismic waves, the energy source required needs to be as large as possible. In order to achieve this, we plan on using the orbiter itself. After it has deployed the geophones and transmitters, it will use its momentum to crash into the surface, creating a large seismic energy source. In order to perform this experiment, we will be using the half of Europa that faces away from Jupiter to reduce Jupiter's influence on the geophones. As straight a line as possible will be used. Orientation is irrelevant because it is estimated that the surface is equally 25 kilometers thick.
The criteria for achieving a successful mission would be gathering relative data about Europa's surface and subsurface by entering valid readings of multiple geophones. An orbiter will be used instead of a lander for this mission, since we do not need to access the surface of Europa. An orbiter is more cost-effective, and using it to impact Europa's surface is an integral part of the mission's success. After the geophones are deployed, the orbiter will impact the surface and create seismic waves that the geophones will record and send back to Earth. Solar power technology has made significant advancements in the last few decades. Before the Juno spacecraft, the efficiency of solar panels was too low to power a large spacecraft into deep space and was reserved for missions within the inner solar system. Juno was the first spacecraft to reach the outer solar system using solar panels as its primary energy source. Many previous spacecraft used radioisotope thermoelectric generators. These generators use heat from the decay of radioactive material and convert it into electricity. The light from the Sun reaching Jupiter and its moons is approximately 25 times less powerful than that reaching Earth. Any solar panels on a spacecraft would have to be able to capture enough energy in these conditions to be able to power the craft for the duration of its journey. Multi-junction photovoltaic cells are currently the most efficient solar cells in production, with over 38% efficiency converting sunlight to energy, compared to around 28% with Juno and 12% in years prior. Radioisotope thermoelectric generators use radioactive materials and therefore increase the hazards involved with their production and are expensive to produce. Solar panels will be used in this mission and serve as a second function by adding weight to the spacecraft. Higher weight is desirable for the impact of the orbiter on Europa, as it will generate a stronger seismic wave than a lighter craft would be capable of. This would enhance the accuracy of the data collected. The Atlas V launcher is best suited for this mission. It has a weight capacity between 10,400 pounds and 19,620 pounds. The orbiter is only expected to weigh approximately 7,500 pounds. The Atlas V has been used successfully as a launch vehicle in past missions of a similar caliber, such as the Mars Reconnaissance Orbiter. Once in orbit, the rocket casing will fall away, exposing the orbiter and allowing it to extend its solar panels and begin charging. It will travel to Europa using the gravity assist method, leaving Earth's orbit but still being pulled by the Sun's orbit. It will come back around and use Earth's gravitational pull for energy, accelerating enough to break free of both the Sun and Earth's orbit, and coast on a trajectory to Europa.
The mission faces a wide range of hazards. For instance, as the instruments travel farther away from Earth, the time required to send and receive instructions would also increase. The increased lag in communication time may lead to failures or crises not being known until well after significant damage has already occurred. Another hazard would be if the instruments sustain damage from small particles prior to collecting data. Small, fast-traveling particles have been known to cause significant damage upon impact, and proper shielding of the instruments is needed. Also, the European surface and atmosphere present quite a large hazard during landing. The lack of a significant atmosphere limits the methods of slowing the geophones during landing, while the highly inconsistent landing surfaces on Europa present the hazard of landing the geophones accurately. Another hazard to the mission's success is that there is no proof of concept of an orbiter impact being used to generate a seismic wave that can be measured by geophones. The mission may fail if the impact occurs, but the geophones do not collect any useful data. The instruments may also be destroyed by solar radiation or radiated particles from Jupiter. The picture on the left shows radiation constantly flowing from the Sun. It's important to note that while the instruments travel from Earth to Europa, it is not protected by a magnetic sphere. As it approaches Europa, Jupiter's magnetic field then begins to protect from solar radiation, however, then also begins to bombard the instruments with radiated particles from. This next picture shows the potential force and scale of an impact caused by a micrometeor. Although small, they can cause very significant damage. This last image shows the potential methods for landing the geophones on the European surface. The image on the left shows the sky crane method used during the Curiosity mission. Although this provides a method of placing the geophones precisely on the surface, the technology is fairly new and relatively expensive. The image on the right provides less precision in placing the geophones but is relatively inexpensive. It shows inflatable balloons which would deploy just prior to the geophones impacting the surface. When the bouncing geophones stopped, they then could prepare themselves to collect data. There is well-established proof of concept in using seismic waves in determining crustal thickness. It was used to determine a wide range of characteristics for the Earth. Also, there is well-established proof of concept in using geophones as a tool to record and analyze seismic activity.